several of us have been working on the work group for quite a while here. My contribution to the picture today is to go into a little bit of detail. Y'all sat through a storage basics presentation having to do with enterprise storage and storage in general. What I'm going to do is spend a little bit more time delving into the details of the very high-level architecture of the resources that we have, typical resources we have in a storage device. And then I'll go into some detail about the characteristics of the workload. So two pieces to the pie here, one of which is the resources that we have to react to the demand. The second facet is descriptions of the salient points of the I/O demand. I will also try and stop after each slide here. So if folks have questions, please feel free to jump in there, because this can last probably about 45 minutes. And if your memory is anything like mine, 45 minutes down the road, I forget what I was going to ask. So feel free anytime at the end of each of these the slides to ask questions. Okay, we talked about a very high-level description of the architecture of a storage device, and here it is. And granted, I will have to admit here that some of these numbers, as Wayne alluded to before, they're a little bit out of date, but the point here is to emphasize the fact that in the entire I/O stack, there are many opportunities for things to get hung up and delayed, and in some cases, we'll talk about accelerated and actually performance improvements that can be made along the way. But essentially what you see here on the left side is the host connected to an adapter, for example, a fiber channel card, an I/O bus inside the device itself, the controller, and then you see at the bottom right-hand side there the actual disks. And in this particular case, those can be, as we talked about, either spinning drives or solid-state drives, or in some cases, a combination hybrid of the two. Any questions? Okay. We talked about the architecture very briefly, and we'll go into some detail later on here in the deck. But what I want to point out here are some of the salient parts of the workload. We talked about the resources that we have to deal with the demand. Let's talk about some of the resources of the I/O demand. And these are industry standard kind of definitions. The block size is the amount of data that we're actually transferring for each I/O transaction. I'll go into a little bit of detail about how we're going to carve those quantums up, if you will. The read-write ratio is important because in general, write I/Os, they're more expensive than reads for a couple of reasons. First of all, a write generally incurs more than one write operation at the back end of the storage device. And in the case, for example, of SSDs, we get into this pathological write state where we actually have to clear hardware pages before we can actually execute the write. Then because of the fact that these treat resources a lot differently, the ratio is important. As a matter of fact, SSDs, you'll see that in general, the writes can be an order of magnitude slower in terms of IOPS than the reads because of the extra overhead that's involved. Access patterns. There's access patterns all over the map. In order to not boil the ocean, we're going to consider two of them, sequential and random. The working set size is the amount of the quantity of space that's traversed during the operation of the workload that's under consideration. This can be a very important parameter as we dig into the advantages of a cache, because in cases where the working set size actually fits in the cache of the storage device and or the server, there will be a significant boost in performance because of the fact that the I/Os are satisfied without going clear to the back end, if you'll recall that other slide, clear to the back end or the right-hand end of that slide. Then there's the I/O demand rate. This has to do with the IOPS that are presented to the storage device in the case of small block IOs, and those are generally less than 64 kbytes. And then for larger transfer sizes, we generally express that demand in terms of MB per second, which is actually the data rate, if you will, of the transfer. Questions? Okay, there's one other very important parameter here, and this has to do with the demand intensity. Some people call it Q depth, but in a nutshell, what it represents is the degree of parallelism in the I/O demand that's being presented to the storage device. Second bullet sums it up. It can be quite profound, especially when we're talking about small block random workloads. The increase in demand intensity will allow us to do fun things like reorder these IOs before they're actually presented to the disk devices, thereby offering economies in head movement, if you will, because if we use an elevator algorithm, for example, to reorder the IOs, we can satisfy several, if not tens or hundreds of IOs through a single traversal of the head across the platters. Unless there is a sufficient IO demand on the actual logical units, the disks themselves, adding more spindles may have no effect at all, because you don't have a sufficient demand to busy the resources that are out there. This can be a bit elusive to try and estimate, and oftentimes it's going to require some human intervention to actually get to the bottom of it. In some cases, this intensity is a programmable parameter that would allow folks like the database administrators and or even the storage administrators to adjust the exerted demand on the storage device, thereby allowing those advantages that I mentioned earlier about the parallelism and the sorting and so forth. So sometimes we just have to consult with the folks that are close to the applications to figure out an estimate of what that Q depth is going to be. Questions? Okay, now let's revert back a little bit to an architectural discussion. We talked about the first slide that we had up there went from left to right, and on the left-hand side was the super fast memory of the host, if you will. And this is closest to the CPU, which means it's going to have the least access time. Okay? Oftentimes these resources, these memory resources, in terms of I/O satisfaction, are under the control of a lazy application, lazy I/O operating system, if you will, that will allow the operating system to hold off on actually satisfying that I/O all the way down that stack that we talked about before, in the hopes of being able to satisfy it without going clear to the right-hand end of that diagram. Okay, this also allows us to do a certain amount of I/O aggregation. We coalesce the writes, we gang them together such that when we do present a demand to the host, or I'm sorry, to the storage device, that there are several of those writes that can be satisfied, quote, at once, unquote. Another optimization is a read ahead. Many databases, Oracle in particular, will allow you to specify a read ahead parameter, which means that when you go out and read a certain block out of a data table, it reads adjacent blocks also. So the idea there is if you just issued a read for location 1, there's a slight chance that location 2 will be in the very near future, and it won't have to go ahead and do the traversal of that diagram that we talked about earlier. The cache controller is the next step in the process, and this cache controller here I'm referring to is actually in the controller itself. It's outside of the host. It's in the storage device. They're very fast. The data access is very fast. However, it's very small. And this is good for frequently accessed data. It's an LRU algorithm, least recently used. If you access something, chances are you're going to access it in the near future. That's what drives the operation of that particular resource. In terms of reads, it will help some workloads, but the real important advantage there is in the prefetching of the reads and in the sequential write coalescing. We build them into blocks, if you will, larger I/O blocks as they go through the cache in hopes of getting more data transferred per I/O. Okay, and we'll talk about write back in a second. And at the bottom of the page here, and at the right-hand end of that previous diagram, these are where the disks reside. And relatively, they're slow, but they're large enough to hold the entire working set size and relatively inexpensive. Questions? Here is another picture, if you will, on in a little bit more detail in this case, of the diagram that we looked at, the first slide that we looked at in the deck here. This shows several applications operating in parallel. And what you see here is a couple of different queue depths that are depicted there. The column in the middle, in the top on the host, depicts a queue depth of only one. It's single-threaded. One gets posted, the others are queued until the posted one gets satisfied, then the next one is taken out of the queue. To the left of that is a queue depth of 2. Here they get posted 2 in parallel, quote unquote. Okay, and the idea there is that we allow some downstream resources to do sorting and optimization on these so that we can satisfy a given I/O with a smaller amount of expended resources. And then the one on the right shows a queue depth of 4. Here we see that 4 of them are posted, and as these are completed, the next one is pulled off the queue and submitted to the storage device. These are all funneled into the storage device through, for example, a fiber channel path. And the bottom portion of that diagram shows you what the storage does when it is exposed to the I/O demand that's exerted by the host above. Again, the idea here is things, if you'll notice, they get kind of reordered and intermingled. That's something really important to keep in mind if you're talking about parallel sequential streams, because remember, sequentials can be optimized in terms of write coalescing and read aheads. But if they're all jumbled together like this, it can render a sequential pattern as being random in terms of what the storage actually sees. And I won't go into detail about the numbering and so forth. The bottom line is that they're serviced in roughly the same order that they're being requested from above. The important thing here to remember too, and this is something that's guaranteed by the storage device, these I/Os really can't pass each other unless they get coalesced before they're returned to the host. Questions? Let's talk a little bit about cache. And the reason I bring this up, Chuck, why do you keep harping on this? In the case, and we're going to talk about the differences between the block device test and workloads and the file access test and workloads. There's a lot of optimizations that can be done in a file-based workload that are not all available when we're talking about block type of demand, block access demand. There's several levels of caches, as we alluded to before. Some of these caches reside in the host. Some of these caches reside in the storage itself. Some of the caches actually reside on the disk drives themselves. There's actually a cache on the disk drive controllers, not the array controllers, but the disk drive controllers that allow one last pass at doing optimizations and so forth. So there's performance gains that can be gleaned along the way, almost every step of the way. But here's two of the biggest benefits. Okay, we have an improvement at the top part of the diagram there. These are write optimizations. This is the write coalescing that we talked about, and this is also representing the read hits that we're able to obtain through locality of reference. Down toward the bottom part of that diagram, okay, we see that the benefits of the buffer pools. And in the buffer pools, the majority of the writes can be satisfied as soon as they are reconciled into a non-volatile cache, which means that your I/O doesn't even have to hit the disk in the case of that diagram that we talked about, the front of the deck. It could be satisfied out of the cache in the array controller itself. Much faster response times. And then later on, that write can get destaged to the disks as the controller operating system sees fit. Questions? Okay, let's talk a little bit about the benefits of a write-back cache. A write-back cache allows us to acknowledge a write back to the host, the application, if you will, after that write has been secured in some sort of stable storage media. It could be battery-backed RAM. It could be SSD front ends to spinning drives in a disk array and so forth. But here you see that without the write-back cache, you have to wait until the whole thing gets satisfied out to the back-end disk, if you will. With the write-back cache, because it's satisfied, it appears to be acknowledged back to the host as soon as it's rat-holed in non-volatile cache. You can see the time saved there at the bottom. Now, the interesting scenario there is you can imagine that if you exert a high enough I/O demand, that your bottleneck won't change, because when you begin busying the back end, you can't destage it any faster than the disks can handle it. So, and that's the reason that we went into the discussion about the queue depth, is that if the queue depth is deep enough, these two curves, these two charts, if you will be one and the same, because it's back-end bound. Questions?
Chuck, this is Wayne. I just want to let you know that I have everyone muted, and if they have a question, I'm watching the chat window.
Oh, thanks, Wayne. Thank you. Okay, fair enough.
I'm in, and I guess you're doing a good job.
Either that or they've taken an early lunch. Okay. Here's some of the benefits we talked about briefly here. Electronic access speeds. There's no spinning media involved in these caches. It's all RAM and or real high-speed I/O devices that are at the front end of the array. It reduces disk utilization. That sounds like a negative. Actually, we'll talk about performance optimizations. One of the ways that we optimize the performance is to minimize the utilization. Sounds a bit counterintuitive, but if you are reducing the load on the slow part of the I/O stack, you will actually improve the performance. We also talked about the write aggregation. Write overlays. Now, there's an interesting concept there. Modern disk arrays don't all really acknowledge a write hit in the cache. A write hit in the cache is when you've got a segment, a data segment that's in the cache that can be overwritten before it gets destaged to the disk. So it actually eliminates a back-end I/O operation. Some would argue that that's kind of dangerous because what happens if a write comes or a read comes in between those two writes? Remember, we talked about the guaranteed ordering of those IOs. This is what keeps this legal, okay? And also, some of those, the write-back caches will allow you to do some speed matching. There's no sense in destaging the IOs to the disk in a rate that's much higher than the disks can handle. So sometimes we do a little bit of impedance matching there, where we actually throttle the destage rate so that it lines up better with the disk speed. And again, we talked, these should be non-volatile, in that any time that you've got an acknowledged write that has occurred from visible to application space, it should be on non-volatile storage. We'll talk about non-volatile storage in one of the other presentations down the road. Questions? And here's another representation of the improved performance, or the relative performance, if you will, of the existence of a cache in the I/O stack. On the far left side there, you see that's no cache. That's actually being acknowledged by the disks themselves. As we move to the right, you'll see that there are significant benefits from the existence of a read cache. And the idea there is that in many cases, the read-aheads will allow those adjacent blocks that we talked about to be placed into cache, staged into cache before they're actually needed. What that does is that effectively lowers the response time and drastically improves the I/O rate, requests per second. And then remember, we talked about writes being more expensive than reads. Well, here's an illustration of it. You'll see that for a given I/O rate, write I/O rate, the relative response time is a lot higher than that given rate for reads. There's nonetheless still a significant advantage, especially you can imagine if all of this working set would fit in that cache. Questions? Here's another way at looking at the pie. This is a timeline that shows the relative latencies, if you will, from the instantiation of an I/O request out till it gets actually reconciled on the disks. This is cacheless, if you will. These are only back-end acknowledged reads and writes. What we see is there's some controller latency. It's involved there. There's a SCSI controller. Why do you have the SCSI controller in there? Well, many of the modern arrays still use a SCSI backend. They call it SAS, if you will. But there is a SCSI protocol that is handled by the backend that actually goes to the disks themselves. After the IOs are posted to the disk, there's a seek that's necessary, and essentially what that is that's the amount of time that's necessary for the head to move. Remember, we talked about optimizing performance. You can see, it's obvious that there's an advantage if we can do more than one IO per seek. So that would increase the IO rate, decrease the response time, and we'd get a lot more work done per head movement. The blue portion of that shows the rotational latency. This is the amount of time that it takes for the spindle to rotate 1/2 of a revolution. And we see in the 15K RPM case, it's about 2 milliseconds. In the 10K RPM, it's about 3. And so on and so forth, increases as the RPM decreases. This is where we get the no free lunch illustration, in that those large, slow RPM drives are very cost effective, but it's done at the expense of an IO rate. Then there's a transfer way at the end there, way at the right-hand end, and that happens to be about the same for the fiber channel drives. So all in all, you're talking about somewhere between a minimum of 5.5 to up to and including about maybe 9.5 milliseconds in terms of service time on the back end, if the IOs have to be posted to disk. And of course, the SSDs blow all this out of the water. You saw that Wayne had a slide up there that showed a 30 nanosecond. Now that wasn't a storage-based SSD. That was an NVDIMM type of access. Those are almost memory speeds. Questions? Okay, here's another illustration of the trade-off between two of these different RPM drives. You see that the red line is for the 10K RPM. Its overall I/O request rate is going to be less when it is saturated. We'll talk about the saturation here in a second. Than the 15K RPM. And the reason for that is the faster spindle speed allows more IOs per second to be served by the 15K RPM drives. And these response times, one would argue, modern day 70 millisecond response time, applications won't put up with that. But the idea here is to show the relative performance of these, not only relative to each other, but also relative to the I/O demand. The higher the I/O demand, the farther we go up the hockey stick on the right-hand end of those curves. If you want to reduce the response time, you have two choices. You either have faster devices, actually three choices. Faster devices, you decrease the utilization, or go to SSDs. That will drastically reduce the response time. Okay, questions? Here's one more way of illustrating the response time versus the utilization relationship. What this shows is that as we increase the utilization, we also have an increase in response time. And if you take a look at the formula that's there on the left-hand portion of that slide, as the utilization, which is depicted there as U, becomes 100%, i.e. becomes equal to 1, the response time essentially goes infinite. So the farther we can stay away from a saturated back-end storage resource, the better off our response time is going to be, because essentially you lower the utilization and you decrease the response time. We can do that, as shown there on the slide, by decreasing the queue depth. However, there's no free lunch. If you decrease the queue depth to make it shallow enough, i.e. equal to 1, then you lose some of the economies of the sorting and reordering that we talked about earlier. Questions? Okay, so why are we talking about improving performance? What's that got to do with the price of eggs here? Well, as you folks have noticed, one of the measured parameters in our metrics is an I/O rate or a throughput rate. If there are steps that we can take to improve that metric, that makes our product appear to perform better. So the reason that we're going through this is that as you folks are going through setting up and tuning these test environments, there are some hints in this deck that will allow you to increase the performance of the device under test. And again, the first one there seems really counterintuitive. You want to reduce the utilization. Well, if you'll recall the previous chart or the formula, if you pull the utilization further and further away from one, i.e., decrease it, you will you'll end up decreasing the service time, which is what we want to do. You can reduce the device request rate. And how do we do that? Well, we talked about caches. The more IOs that we can satisfy out of cache, the better off we're going to be, because it's being serviced by a faster resource and it's reducing the utilization on the back end spinning drives, if you will, that's in the array. And the way that's the first bullet on there is to increase the requests out of cache. The second way that we can reduce the request rate is the larger front-end cache. So several steps along the way that we can offer improvement. Buffer cache in the server, front-end cache in the array. Another way to reduce the utilization is to increase the spindle count on the back end. The more spindles you have to bring to bear for the given I/O demand, the utilization of each of those will drop accordingly. And then in terms of reducing the service time, same scenario. You increase the cache, use quicker devices. We talked about SSDs briefly. Or there's another option where we introduce the concept of tiered storage, where we have fast and slow devices intermingled on a given array, and then redirect the traffic, the heavy traffic, to the tier that offers the greatest performance, thereby decreasing the demand on the slow tier. That's one improvement, and also satisfying the I/O requests out of the faster tier. Questions? Okay, one more trip around the block here. Improving performance, minimize the disk I/O. Satisfy as many of those I/Os out of from the front end as we can. Another concept that we run into a lot in our data centers is people complain about slow storage. One of the most effective means that we employ to increase the performance of the storage is to spread the load over the resources that are out there. And that can mean more front-end I/O ports, more back-end I/O ports, or simply more disk spindles. The more resources we have to bear to handle the I/O demand, the faster the performance will be. Then we talked briefly about large sequential I/Os. We have to be very careful, as we saw in that previous diagram that had the two Q depths in it. If we interleave enough of these sequential I/Os ahead of the storage, what will happen is they'll appear to be random I/Os. What that does is it defeats the read ahead and also the write coalescing, the optimizations that can be done along the way. And last but not least, some of these systems are pretty good at minimizing the cross pollution of the cache, in that it can keep track of the I/O streams and not interleave them. Questions? Okay, so that's the material that I have. Again, I would like to open it up for any questions or comments that any of you may have. And again, the idea behind this portion of the presentation was to go through somewhat of a high-level description of the I/O stack and talk about the I/O demand and how the two interact. Questions or comments?
I think that most people off mute if you wanted to ask a question.
Yeah, but I assume if it most of let's say most of the time we might have, of the first 6 months we might have anyway suspended the stuff. It means that also, no, I mean that also goes if we would take it on, that also would go down, right?
I'm sorry, I didn't understand.
It could be, and we could remove it, or.
Raining, and it's 53. Welcome to Northwood.
But still two more months. You know what? We add it now and then we later on take it off. Yeah, just a better feeling.
Andreas, if you're able to type the question into the chat window.
Yeah, that was nice to have low price for the best coverage. Yep.
So Wayne, do you see?
Andreas, are you going to type in a question, or are you going to email it? Or
I think Andreas has a side conversation going on, Wayne.
Ah, okay.
With who?
Someone not on the call in his office.
Okay, thank you. Well, Andreas is, reforming his question. Does anyone else have questions for Chuck? I'll ask a question. Chuck, on these basics here, how important are these when you're trying to find the optimal configuration for testing? Is it pretty expensive that you have to do run after run?
That's a good thing.
Yeah, so Wayne, that's the reason that toward the end of that deck we had some hints in terms.
Okay, and it all will show up later on the paperwork then.
Yeah, the tuning
at the moment, and then later on they will get the.
Yeah, we'll have to.
Good, Chuck. I've muted Andreas
because
it seems like he's kept on trying to talk on top of it.
Okay. Yeah, Wayne. That's the idea behind putting the performance, the improvement hints toward the back end of that this deck here. Is that if you're talking in the block workload as an example, offers those couple of different dimensions of optimization. There's the transaction optimization, the small block random workloads, and then there's the large block sequential workloads. Those are going to have two different, not necessarily diametrically opposite, but two different tuning techniques in order to find the sweet spot of those two different workloads. And when we talked about the working set size and the caching and all that other stuff, the big benefit there is going to be on the small block side. The more of that workload that we can fit in that cache, the better off we're going to be. In terms of the sequential workloads, the cache helps to a certain extent, but a very small amount of cache that's being exposed to a sequential workload can have a real profound effect, because the big benefit that you get there is from the write coalescing that goes on. But yeah, in order to find the sweet spot, I know when we did our submissions, when Herb and I were working together on this, we would constantly be going in and looking at resources in the storage devices and figuring out where the hot spots are, and then rearranging the workload and or the storage resources to relieve those hot spots. So yeah, it's really important to understand the various pieces of the performance pie, if you will, that come to bear for these different workloads. And that's how we achieve the sweet spot. You'll also see, because of the fact that we've got a power component in this environment, that there's, again, a no free lunch thing. You add spindles to a certain point. Going beyond that won't make the storage device go any faster, but the power consumption will continue to grow. So what you need to do is trade off the optimal disk count, which may be nowhere near the supported maximum of a given storage product, to find out where that power performance curve develops a knee, and then narrow in on that knee, and that's what you use in terms of the configuration that you submit for certification.
And I know over time, as the EPA moves forward to maybe establish thresholds, having a finely tuned system may make a difference whether or not a particular test run will be eligible for an Energy Star label or not be one. And I was going to say, is there a community that you performance engineers hang out in, that you share knowledge without revealing secret sauce of one's product with your vendor?
So, with many of these organizations, this one included, our mindset is you leave the marketing guns at the door. And what we've done in the past, and it's happened, like I say, in this group and in the Storage Performance Council also, is that we will coach and help each other to optimize, our test results, but not necessarily to the point where we disclose secret sauce and so forth. So yeah, we do corroborate as a group behind the scenes in almost all of these performance-oriented organizations.